So let us take a few more questions and answers in data structure and algorithm. Why do we use asymptotic? Use asymptotic or asymptotic notation in the study of algorithm. Describe commonly used asymptotic notations and their significance. Asymptotic notations, they actually tell you about the bounds, upper bounds, lower bounds. So these are the bounds. That is why we know we want this asymptotic notations like say big O, omega, theta, etc. So the running time of an algorithm, it depends on various characteristics, and slight variation in the characteristics, it varies the running time. Running time is the time required by the algorithm to run to its entirety. The efficiency and performance of the algorithm in comparison to some other algorithm for the same stuff, it can be described by the order of growth of running time of an algorithm. What is this order of growth? Suppose we have one algorithm for a problem that has a time complexity, say this number. I'm not specifying any number. And another algorithm which has some, say, this number. It can be anything. It can be n, it can be n squared, it can be cn cube, anything. Then it can be easily observed that this algorithm, this first one, will be faster than the one with complexity this. Why? Because this has considered it to be of the power. So it is n square, and this is having n cube plus n square. So it is order of n cube. So we conclude that the first one runs faster than this one for sufficiently large values of n. Now you have to very well understand that we are talking about sufficiently large number of n. We are not talking about n equal to 10 or n equal to 100 or n equal to 1000 or 10,000. We are talking about large values of lakhs, 10 lakhs, and more than that, millions. So whatever be the value of C1, C2, C3, all these constants, there will be an n beyond which the algorithm with complexity C3n square is always faster than this C1 n cube plus C2 n square. So we refer to this n as a break-even point. So it is difficult to measure the correct break-even point analytically. What we are talking about is, we are saying that this n, where this break-even point we are suggesting. So analytically, it may not be we may not be able to find it. So we employ asymptotic notation, and this asymptotic notation were introduced that describe the algorithm efficiency and performance in an understandable, easy, and meaningful way. So these notation describe the behavior of time and space complexity for large instance characteristics. So these are the asymptotic notations we commonly use. This is the most common, big O, then big omega, big theta. Do we have another? So before going to next question, let me tell you, we also have small omega, small theta, and small order. This is O, big O, so we have also small O. But there is a slight difference between these three and those three. I'll tell you in the course of discussion. First, let me tell you about this big O notation. So the upper bound of the function f is provided by the big O notation. That means if this is your function, the upper bound means this function will always be on the upper side. Your function will never cross this function. So we call this as the upper bound of your function. So upper bound of a function f is provided by big O, and if you consider g to be a function from the non-negative integers to be positive real integers, we define order of g as the set of functions f such that some real constant c is greater than 0 and some non-negative integers n0, fn will be guided by gn, or g1 will be guided by fn, say, for all n which is equal to n greater than n0. Mathematically, order of gn is equal to fn. There exists positive constants such that order of fn is fn which is greater than gn for all n equal to or n greater than n0. So we say f is big O of g. So before going to omega and theta, this definition, let me tell you this definition, so you'll be able to understand these two very easily. Say you have, this is your function. Now there is some other function. This is your function, yours function. Now see, in the previous, for this n0, before n0, this function which we are considering to be the upper bound of your function has gone below your function. So we will not take these points, these n values. We are talking about n0. So this function For this function f, if this function is gn, so gn will always be greater than or equal to fn, your function. This is your big O. So big O of gn we say. And then there is another function which is always lower than your function. This is the lower function. So we say this function or your function is big omega of this function. Why? Because omega means you are talking about those function, that function which is always less than or equal to. This function big O means always greater than. These are pre-described functions. Means there will be n square, they can be n cube, they can be log n, they can be n log n. So these are pre-described functions. So your function is guided by these functions. These are the asymptotic notations, asymptotic bounds. And if certain function is there which has both upper and lower bound which guide your function, so that is big theta notation. So big O and small o varies like that in this big O notation, your function can touch the above function. It will not go beyond, but it can touch. But small o says that your function will never touch this also. So it will always be, this gn will always be greater than your function, not greater than or equal to. Greater than or equal to means you're talking about big O, and you're talking about only greater than, then you're talking about small o. And similar for these two notations. Illustrate the steps for converting the infix notation into a postfix expression for the following expression. So you have an expression, you want to convert it. This is an infix notation. You want to convert this into postfix expression for this expression. Okay. So let us see how we can convert it. First is, as I said earlier, we have done this type of question. We'll be doing it again later discussion. So first is that you have to see the precedence order. First precedence is your bracket. So we'll see the bracket. First is a plus b. So a plus b bracket means what? And you have to make it as postfix. So post means this operator will be postfix. This operator will be fixed in the after the operands have been written. So it will be a b plus. Okay, now this is done. A b plus. Now you'll deal with cd. C, D and plus in the same logic goes here. EF plus, same logic. Now we have converted these. After this, we'll see we are left with into and division and this exponential. The precedence of these three operators are like this. First we'll deal with exponential, then division, then multiplication, and then division. So let us do in this fashion. What is this? This is exponential. EF plus is one operand, G is another operand. So and this is the operator. So how we will write it? EF plus, then the second one G, and then the operator. We have to post fix this operator. So this is also done. Now we are left with multiplication, division. So as I said, multiplication has the greater precedence than the division. So we'll apply this. First operand is this, second operand is this, third the operator is this. So we have to fix this operator here. After this, first we write AB plus, then CD plus, then into A. Now we are done with these two. Now we are left with division. So first operator is this, first operand is this, second operand is this, and then the division the last. So this is the postfix operation of this given infix operation. I hope you got the idea. How you represent a max heap sequentially? Explain with an example. Max heap sequentially. So you know what max heap is? It is a tree in which you have the highest element at the top, that is at the root, and all the elements. And because it is a binary tree, all the elements in the other tree, other nodes, they are always less than the root, and this goes recursively. So max heap, also known as a descending heap of size n, is an almost complete binary tree. We'll see in later questions what is almost binary tree. So almost binary tree of n nodes, such that nodes of each node is less than or equal to the content of the father, that is the root node, or any node which is the root of the subtree. So the topmost will be higher than other subtree nodes, and recursively it goes. That means this is true for this also, this is true for this also. Why we call it as an almost complete binary tree? Because it goes like this. First we fill this like this, okay, then we fill this, then we go here. So say if I want to just add two more, we'll add these two only. We'll not add these two nodes here or here. We'll start, or we'll fill it as left as possible. All upper nodes needs to be filled with, or they should have at least two subchild or two child, and the order should be as left as possible. The filling should be as left as possible. Well, why we require it? Why we require it? Because see, if the sequential representation of an almost binary tree is used, the condition will simply reduce to the inequality that info j, if this is an array, info j is less than or equal to info j minus 1 by 2 for j minus 2, which lies between 0 and n minus 1. These two lies between 0 and n minus 1. So it means info j should be less than or equal to info j minus 1 by 2. So it is clear that this definition that the root of the tree contains the largest element in the heap, in the descending heap for any path from the root to the leaf is an ordered set or list in the descending order. Let me tell you one more thing here, what exactly I mean. Let us take an array. Okay. Now I place one value. So the second value will be 2i at the 2i position of the array. The other will be 2i plus 1. Means if this is the root, the next position with respect to this root will be 2i and this will be 2i plus 1. So we know exactly 2i and 2i position. So this is how we make a heap sequentially, because we are placing the value in the array and we are able to retrieve it also just by dividing. Okay. So this is the condition, and this is how I showed you. Write an algorithm to insert an element to a max heap that is presented sequentially. This is just an addition of this question. So this is a new key. We want to insert a new key to max heap, say of size I minus 1. So in this, we would try to find out S div 2. How we can find out the if we are at this node. I told you that the two childs can be known by 2i and 2i plus 1 in the array. But if we are at this node, how we can find the parent? This is done by as division 2. So 2i, that is, we divide by 2, take the floor or ceiling, you can get the parent. So for each parent, which is S, that is the S you want to see, S division of 2, and this new key will be entered into this key S. So while this S is greater than or equal to 0 and key parent is less than or equal to key S, we interchange the parent and child. Okay, we insert an element in max heap and we interchange these. You know how to interchange, that is a swapping, and then we again divide it. So what we are trying to do here is we are trying to insert an element to a max heap that is an array, and we know that there is a possibility. If you are not able to understand this, don't worry, because we know that what is the parent. We can go to the child and we can know the parent, and if the parent is not, we can go to the children. So we can easily insert the value wherever we want, and we want to insert an element. That element can be compared first of all, and if it is compared, it has compared and find its particular position just by finding the parent. You can just add it. Okay. Construct a binary tree whose nodes in order and pre-order are given as follows. So this is the answer. I hope we have covered this type of questions now. So you can easily, this is a binary tree. We have a binary tree with in order and pre-order which is given, and we can easily find a tree. And we'll see if we can directly make it. It is okay. Otherwise, in coming questions, we'll see step-by-step formation of binary tree in the elements which are given. Execute the algorithm for infix to postfix. We have covered this also, but we'll see how it is done for this particular expression. So this is the expression, and we have to execute an algorithm to convert an infix into postfix with your infix as this. So what we'll do is, because these are brackets also, first of all we have a symbol, that is the round bracket starting. We place it into the stack. Okay. Now we have a symbol M. So what we are going to do? What we are going to do? Stack will contain this, and postfix expression will be M. Always when the operand will come, we'll take it as a postfix, writing in a postfix expression. Next expression, say token is what? You know, these are tokens. They can be operand, they can be operator. What is the next token? That is plus. Now this plus has come, so we'll add if it is a token. If it is a token or an operator, will place it on what? Stack. Otherwise, if it is an operand or a variable, we'll place it on the postfix expression. So plus has come, we'll not place it here. We'll place it on the stack. What is the next expression or next token? That is plus. Plus has come, so we have added it. Next is n. N has come, and you know that whenever a variable or a token of this type will come, We'll not place it on the stack, we'll write it here along with the previous one. And now we are confronted with the ending bracket. So we know that this has come and now the round bracket has come. So what we are going to do, we will empty the stack, means we will take out this plus, place it here, and then we'll take out the round bracket also, and we'll just make it empty. Now we got the matching, so we'll remove these two, but the plus will be added here. Okay, now you understood. Next is into. Next into has come. So you are aware what we are going to do. This into needs to be placed on the stack. Then the round bracket has come, so let us place the round bracket after this into. Then k has come. What k will do when the k has come? We know that whenever variable has come, we will not place it on the stack, but we'll place it along with the postfix expression. So we'll place k. Now plus has come. When plus has come, you'll not do anything, you'll place it on the stack. We are waiting for the ending round bracket. Next is p. So no problem, p will be placed in the postfix expression. What is the next one? Round bracket. Now we have the round bracket, the ending round bracket. So as the round end bracket will come, we will take this plus, we'll place it in the postfix expression, and we'll remove this round bracket also. So only this into is left. Into is left. We'll keep it like this because we have to go after this, because this will come after. What about this division? Now division has come. What of division? We have into also, round bracket also, so we have to take into also, and we have to keep it here, right? We have kept the into, now the round bracket has started. First division has come, so we'll place division in the stack. Now round bracket has come, we'll place the round bracket also. Now g has come, we'll place it here. Now division has come, we'll place it here. B has come, we'll place it here. Round bracket has come, means end round bracket has come. So you know what you have to do? You'll pick this one, place it here, and remove this initial round bracket. So you are left only with the round bracket, means division. Let us see what has come. What will come? You have this value or this operator. So let operator can come. Let it be there. We'll take it as an operator. Round bracket has come. Keep it there. Variable has come. Please keep the variable. And then D has come. Let me put D also. Division has come. As division has come, this division, what are you going to do with the division? Because you have division here also and division here also. So in this case, as this has come, we know that this particular cap or this exponential has the higher precedence. This has higher precedence than this division. So we'll take this out, keep it here, and other thing will remain the same. C has come, we'll place C. Then what has come? Round bracket. And you know what you have to do? We'll take this division, keep it here till the end round bracket. And we are left with these two. So we'll take one by one, cap here, that is exponential here, and division here. So this is the final formation. So hope you got this idea how you can use stack to convert an infix to postfix. What do you mean by hashing? Explain any 5 popular hash function. So hashing provides a direct access of records from file, no matter where the record is in the file. So this is possible with the help of hashing function h, which map the key with the corresponding key address allocation. Hashing is a method or direct access to a record from a file. So this is possible with the help of hashing function. We'll see the hashing function. Different hashing functions are there with us, which will map the key with the corresponding key address of the location. So it will provide you the key to address information like this. Let us see. 5 popular hashing functions are like this. First is the division method. This is the division method. An integer key x is divided by the table size m, and the remainder is taken as the hash value. How can it be defined? The hashing function can be defined as x is divided by the table size. Say table size is say 7. So whatever value will come, say 1, 2, 5, 6, all this will be divided by 7, and we'll be placing it, and the remainder is the hash value. For example, x equal to 42. What we are going to do with this? And x is 42 and m is 13. So let us place it in this formula: x modulo m plus 1. So 45 modulo as 42, 45, and 42. This has come as we divide 42 by 13. This is not 45. This is 42 only. 42. 45 modulo 13, that will give us the remainder as 3, and because 13 3s are 39, so 3 will be the remainder. 3 plus 1 is 4. So what for this hashing function for 42 will be 4. Let us take one more hashing function, that is meet square method. In this, what we do, a key is multiplied by itself. A key will be multiplied by itself, and the hash value is obtained by selecting an appropriate number of digits from the middle of the square. The certain positions in the square must be used for all keys. Let us take an example. If the key is 1 2 3 4 5, say, what is the square of this key? 1 2 3 4 5, multiply 1 2 3 4 5 into 1 2 3 4 5, that will be this value. If 2-digit address is required, then the position 4th and 5th will be chosen. If 2-digit address is required, we'll take the position 4 and 5. So what it will be 39. So this will be the address. So let me tell you again, meet square means we multiply a key with itself, and the hash value will be obtained by selecting an appropriate number of digits from the middle of the square. So we have chosen this 39, and this will be done for all other. Then next is folding method. What is this folding method? A key is broken into several parts. Each part has the same length as that of the required address except the last part. When the parts are added together ignoring the last carry, we obtain the hash address for key. Multiplicative method. So this method, a real number say C, which belongs which is between 0 and 1, will be selected. That can be 0.2, 0.7, 0.8. And for a non-negative integral key x, the hash function will be something like this. This will be m into cx modulo 1 plus 1. So this cx modulo 1 is the fractional part of cx, and this denotes the greatest integer which is less than or equal to its content. Okay, this is the greatest integer function. You know, the ceiling and floor in programming, that is exactly this. So this is the multiplicative method. Next is digited analysis. This method forms addresses by selecting and shifting digits of the original key. Let us take an example. For a given set, you have a key set. The same position in the key and the same rearrangement pattern must be used. For example, a key is 7 6 5 4 3 2 1. This is transformed to 1 2 4 7. 1 2 4 and 7. So we have selected the digit in the position 1 2 4 and 7. Okay, then by reversing it. Okay, so this is what we have seen as hashing. What is the best case complexity of quicksort and outline? Why is it so? How would it worst case behavior arise? We have seen that quicksort can give you an order of n log n, which is comparable to the best we have, which is the merge sort. So this gives you order of n log n sorting efficiency, that is the big O of n log n. This is the best complexity quicksort can give. How could it worst case behavior arise? Let us see. In the best case complexity, the pivot is in the middle, just like merge sort. So if this is the list, the pivot is in between. And to simplify the math, we assume that the two sub-files are exactly half the size of the original. So it may give slight overestimation, but this is acceptable because we are only interested in big O, that is upper bound. So it can be divided into, if it takes tn time, this is what? Tn by 2, Tn by 2, this is again Tn by 2. So how much this is? 2 Tn by 2 and Tn by 2 is 2 Tn by 2. And the time and the Cn is the effort required to break it into Tn by 2. This is the effort to divide and divide partition. So partition will require this much, and this 2 Tn by 2 will again recursively done. So the total time will be 2 Tn by 2, the two parts plus Cn of the time which is divided, which is required for this pivoting, etc. So this if you combine this, or if you evaluate it using some back substitution method, this will be C n log n plus n, that is V n log n. Order of n log n will be the answer, or this will be the best case complexity. Worst case will be the pivot is the smallest element all the time, then I equal to 0. So we ignore T0. We ignore that T0 equal to 1, which is insignificant now. So the recurrence will only be Tn is equal to Tn minus 1 plus Cn. Why? Because the pivot is taken as the smallest element where n is greater than 1. So if you find the complexity of this expression using back substitution, it will be nothing but the order of n square. Okay, because this Cn, it will be from 2 to n, sigma will be from 2 to n of I, and that will be nothing but the order of n square. Explain the Dijkstra algorithm for finding the shortest path in a given graph. Dijkstra or Dijkstra algorithm is a shortest path finding algorithm for that can be employed on a graph. In this, what happens? There are multiple nodes. These are nodes, and if I want to reach from one node to this node to this node, and there can be multiple paths. This can be one path, because this can be another path, this can be another path. So which one of the path is the shortest path? This is given by Dijkstra algorithm. And the way is to choose. We first assign all these nodes value of infinite, and then we try to seek every next vertices. We'll see the algorithm just now. So the problem is concerned with the finding the low or least cost, because all these edges, what we are seeing here, they are weighted. These edges, they are weighted. They have some weight, Wi say. And least cost from the originating node, this node, in a weighted graph, to a destination node in a graph. So these paths are weighted. So they have certain weight, and we have to find that path which has the least weight. So the algorithm will be something like this. We have a graph G with vertices and edges. So let A and Z be any two vertices of the graph A and Z. And let's suppose Lx denote the label of the vertex S, which represent the length of the shortest path from vertex A to vertex S. And this Wij is nothing but the W sub I. These Ij are subscript. So Wij denotes the weight of the edge. So Eij edge Eij will be equal to from Vi to Vj. I and J can be any of these two. So let us start. Let P will be where P is the set of those vertices which have permanent labels. So T is the all vertices in the graph. So set L equal, we start with the 0. So let L be equal to 0 and Lx, this is for all xa. Select the vertex V in this T which has the smallest label. First we have to see the smallest label. This label is called the permanent label of V. Also we set P equal to PV and T equal to T minus V. If V equal to Z, then this Lz, which is the last one, is the length of the shortest path from the vertex V A to Z, and we stop here. If V is not equal to Z, then we revise the labels of vertices of T, which that is the vertices which do not have permanent labels, and the new label of vertices X, it will be given by minimum of old Lx plus Lv plus W weight of Wx, and this Wvx is the weight of edge joining vertices V and X. This is the weight from V to X. If there is no direct edge joining V to X, then we take Vx, this weight to be infinity. And we repeat it again and again until this Z gets the permanent labels, that is the shortest path. Define B tree. B tree. B tree is balanced tree. This is balanced binary tree, you can say. It is not a binary tree, it is balanced tree. So just as AVL trees are balanced binary search trees, B tree are balanced M-way tree. Now every node can have M keys here. So this is not BST, balanced search tree, but it is M-way balanced search tree. You can assume it like this. So it is a balanced M-way search tree, and a B tree of order M is either the empty tree or it is M-way search tree with the following properties. That is, each non-leaf node has a maximum of M children and minimum of M by 2 children. Each leaf node, tree has they have internal node also, they have root also, and they have the leaf node also. So all the non-leaf node which are not leaf has a maximum of either M children, and maximum is M, minimum is M by 2. And this is an integral division. So each node has one fewer key than the number of children with the maximum of M minus 1 keys. And keys are arranged in a defined order within the node. So all keys in the subtree to the left of the key are predecessor of the key, and those which are right of are the successor of the key. And all leaves are at the same level. So these were a few more questions on your data structure algorithm. We'll be seeing more. Thanks so much.